Hello and welcome back to compiler programming. Today I'm going to be touching on one of the most complicated topics in the compiler design or language design, and the topic that countless people spend thousands of hours poring over it and trying to write computer science papers, trying to optimize and trying to figure out what is the ultimate way how to do it. It's also sort of an unsolved topic in computer science. Like nobody can tell you like what is the best way to do it, and if we could achieve the kind of ultimate way to do polymorphism, which is what this video is all about. So I'm gonna start very simple. The first thing we're gonna talk about is why do we want it, and what types are there, and how we can approach this in the design. So in C, which is what I'm using to write this compiler, there is really no polymorphism except for like very basic operations. So operators like plus, minus, and so on, they are actually polymorphic. Because if you think about it, like let's say I have 5. Let's write a maybe simple function. Let's go to our tests and just add a test randomly somewhere. Doesn't really matter what it is. Should support parametric polymorphism, if I can type polymorphism. And I will talk a bit more about what parametric means. So if we think about C, as I said, and we create a variable, so we have a byte, and that byte is 15. And then we have another thing, which is we say this is user32, this is a byte, this is user32, whatever integer, and we say this is blah blah blah. Then we can do whatever u32 result is integer plus byte, and I have to acknowledge that I'm not using result, otherwise compiler complain, right? So if you think about it, C accepts this quite fine, right? It says, okay, you can take a 32-bit value and add a 8-bit value, but I could also say U16. Let me call this other, so that I'm not lying about it being a byte, right? It's also fine. There are obviously combinations that are not fine. If I put U64 here, it will complain about loss of data, but this is just a warning. So if I didn't have warnings enabled, this would also be sort of fine for the language itself, right? And this is actually not what's called polymorphic. This means it's an ad hoc polymorphism. And there is an article about it on Wikipedia, which I will link in the description of the video. But essentially this, if you know C++, this is overloading. You define a function, or you define an operator that can accept different type, right? In this case, it's very simple. It only accepts integer types, or it also accepts function pointer types, right? In C, you can add to functions, or to pointers, sorry. But it is polymorphic. But for users of the language, in C at least, you cannot define your own polymorphic functions that would be at least checked at compile time. You can do some weird tricks with void star, but this is a different topic of conversation. If you read in C++, you know that you could do something like int foo of int, right? And then you can also do, say, int foo of some reference to struct foo. And depending on what you pass into here, C++ will decide which of these functions to call. And there are certain rules, like, for example, you cannot do something like this, I believe. So if I do S16, I'm not sure, like I can't test because it's not C++, but I believe it will disallow it because of the way integers are promoted. Like it will not be able to decide which one to call, at least if you call it with a literal. And also it obviously disallows to do that. So because it won't really know which version are you planning to pick, right? They are exactly the same. They have exactly the same signature. And for polymorphic functions, at least for ad hoc polymorphic stuff, this is the deciding factor, right? Are the arguments sufficiently different that compiler can figure out which function you actually meant? There is all kinds of complication that goes in there, depending on the language design, but in the simplest form, this is what it is. Okay, so this is a very quick tour of ad hoc polymorphism. There is another kind, which is let me bring this back to U16. So it compiles. Another one is Parametric. And this is where you provide type as a parameter to the function. In C++, this would be template functions. Again, in C, there is really no concept of parametric polymorphism. I think in C11 they added they added some ways for numbers to do that, but not really. So in general, there is no way. But the idea is pretty straightforward. Again, there is an article on Wikipedia. It's a bit mathy and functional programming oriented. So depending on your background, it might be a bit tough to read. But the idea is that you say, okay, I have some kind of type, and I'm performing an operation on that type, and it doesn't really matter for me what the type is, as long as this type fits into certain constraints. And in these constraints are usually generated from the body of the polymorphic either function or struct or whatever is you're doing polymorphic. So as let's say we have an abstract syntax for this. Again, C will not support this, but let's say I'm writing C++. So I think whatever it's called, template, type name, A, whatever, right? And then I do int foo is a, and I say return a to int, right? So if you look at this body, if you try to instantiate it with some type name, so you say I call it like, I don't know, with type foo, and I pass some foo. Foo, whatever is the foo, right? And I pass it. Usually in a lot of languages, you don't need to explicitly specify the type parameter if it is inferable from the arguments. So it's in this case, like compiler knows, right, that if you pass in foo here, then that means that A is foo, and even if you have like multiple things here, then it still will use the same type. But I digress. The idea here is that even though we don't explicitly specify constraints in this case, there are some, right? So the first constraint that if we ignore this, if we just look at this definition, so let me spread it apart so it's a bit easier to concentrate on this. The first constraint is that A is a class, right? It's or struct, which are basically the same in C++, because I'm doing dot on it, right? And you can't do dot in C++ on struct things, right? You can't do 5 dot something. I mean, some languages allow you to do it, but not in C or C++. The second thing is there has to be a method on that class that is called toInt that accepts no arguments, or one of the overloads of it accepts no arguments. And the return type should be implicitly convertible to int, or I mean, basic, you can say just int, but it can also return, for example, S8 or byte. As we see here in C and C++, there is integer promotion. So you can always kind of go up in size of integers. So this could return 8, 16, or 32 bits, and this would be perfectly fine. And the way this generally works is the compiler would create a copy of this function with that type, right? So it will remove this thing, and let's call it foo, right? So we kind of append a version, or if we have ad-hoc polymorphism that we don't even need to do that. So we have overloading, and we say foo a and a to int, right? So it literally just took this thing and substituted it here, and this is also how it does that type check, because it tried to work on foo, and if foo has to int, then everything fine. If foo does not have to int, it will be like, sorry, you can't actually do that. This is not a valid code, so you're wrong. In modern C++, so probably 17, actually, I think they introduced in 20, like you have other constraints, which are concepts. I haven't really used them in almost at all, so I don't want to talk about them. And previously you could do hacks, at least in C++, to introduce other constraints, like saying whatever this type A, for example, it's an integer or whatever. But the general idea is you have a function, and it accepts a type as kind of a higher level argument to itself, and you substitute the type in wherever it is used. So I can also do like a temp is a, right? And I can do temp to it. This is also perfectly fine, because all of the a's will be substituted. So again, you pass this type, and then you have some constraints on the type that determine if this is okay to pass the type or not. Okay, so with this very, very brief overview out of the way, because there is a bunch of stuff, there is once you go into the whole polymorphism and types, and it's a very deep rabbit hole, especially if you go into functional languages like Haskell. There is a lot of research on that, but we will stick with these two things because majority of modern programming languages support some kind of mixture of those. And as that, I made examples with C++, so C++ obviously supports both versions, Java, Scala, I don't know, Rust to a degree. I mean, Rust has traits, which is how it implements ad-hoc polymorphism, which is like one of the versions how you can do it. So there is a lot of variety here, and it's really up to language designer to figure out what would be just the right combination, because as I said, in pure mathematical or computer science, nobody really knows. Nobody can tell you like what is the right answer here. And to make matters worse, if you have both of these, because there is no right answer, you end up in a situation where behavior is weird. Like it's either unknown, like you write some code and depending on some other code, it can do different things. Or it will not compile at all, even though you think it should. Like it makes sense to the human, but it doesn't make sense to compiler. So there is a lot of kind of weird corner cases once you go into this topic. So we are gonna do our best, but you can't tell how good our implementation is. Okay, And I will actually start with parametric polymorphism, because in the way we set up the code so far, we can actually cheese it. And our support for parametric polymorphism is going to be ridiculously easy. So what do I mean by that? And we were actually sort of doing it from the very first episode, if you think about it. Because as I said, the idea about parametric polymorphism is that you accept a type as kind of an argument to the function, as a high-level argument. Not something that will be used at runtime, but something that compiler will use to generate the function for you. And since we generate the functions already, what we could do is we could have a polymorphic function very easily. Let me just bring this code up a bit so it is easier to deal with. The way it looks like, we just need to write a function. We will have value star, and we will create a polymorphic identity function. So, which means that it will take any value and return us the value of the same type. But it will kind of create a new function every time. Let's say, so make identity. And what it accepts is it will accept a descriptor of the type. Okay. What it will do, well, we will need a function. So as said, like when you deal with parametric polymorphism, you have functions that create essentially functions, or you have compiler create functions. And since we are in C environment, we are choosing it by just using C as that extra step to create those functions. Okay, we say argument is going to be X, and the type of that argument is going to be type. And then this function is going to return X. And then we return the function. Okay, that seems like that should work, right? This is nothing new for our code. We didn't even have to add any features to it. So let's see if that actually does work. We say we'll need our weird type definitions for functions. Actually, no. Value star ID S64. Okay, ID S64 is make identity of descriptor S64. So we are, same as with that example in C++, where you had template. Here our make identity is writing is that template. It will create our function. Okay, so let's check if we can actually use this, right? So we will need to create another function that will be our test function. Now we can't just call it from C because it will not check that the types are correct. So we will need to call it from our world. And we say check. Okay. And what this will do, it will just call function value. I definitely need to fix this stuff. But for now, that's fine. So we have value star value. So int 64 or value S64, value from S 64. It doesn't really matter what the value is. We can use 0, we can use anything else, because right now we're just looking at types. And we say value as 64 and 1. And we don't actually care about the return value of this. We just want to know if this actually type checked. And we don't even need to call this function again. We are interested strictly in like, is this a valid thing for us to do? So let's run the tests and see what happened actually. I probably need to first check if I did it the right way. Too few arguments. Yes, we also need to pass the actual function that we are calling. Sorry about that. Okay, now I can run the tests and I expect to see that everything is fine. Now, to verify that it actually might not be fine, so I can inline this thing. And let's say I will pass S32 into here. So this naturally explodes, right? This assertion is inside of call function by value where we do our type checking. That was implemented in last episode, I guess. Okay, so we know that at least our type checking works, but now we can create other functions as well, right? We can create identity S32 and we will pass now another thing to identity S32. Okay, so this is kind of really the essence of parametric polymorphism. You pass in the types and you create new functions based on those constraints. Now, there are obviously more consideration to be had. One of the things is we are not doing any operations here, right? So in this identity function in functional programming would be written like this. So it accepts any type A and returns that type A. In C++, I guess it would be like template, type name T, T ID, T, right? So it accepts this type and returns this type. And so this would be the implementation in C++ of this. But is it like it doesn't impose any restrictions on the types that are passed to it. So what if we introduce some? Okay, how would that look like? Make add 2. So now again we are creating a function. It can be called add2. Doesn't really matter how it's called, but just for our convenience, it accepts an argument of the type, and then what it returns is plus of x and value from S64 of 2. And I mean, this is actually our first problem, that our numbers are not polymorphic at all, which is not sort of how, for example, UNC works. If you type in the number like this, the actual type of it will be determined by what it is assigned to or how it's passed, right? So this will only work for S64 right now for us, but it still illustrates the point, because the presence of this operation will add a constraint on which kind of types we pass, namely that should be the type that can be present in the sum on the left side with a 64 on the right. And let's do that as well. So we say make add2 and we call it add2 S64. we pass S64 as a descriptor, and we can call this. So call function value, add to S64, and let's start with a broken one. So this will explode because we pass S32 to it, right? At least it should. Yeah, it explodes because our type that we pass does not really like satisfy the requirement. Or more precisely here, it fails in arguments, I guess, but for our purposes, it is sort of one and the same. I mean, we could also create like a stack variable with that type instead of an argument to illustrate the point. Well, let's do that. So we accept an argument, and that argument, no, I will not go into this because we also need to then figure out like abstract types, but we will not go into this. Let's stick with concrete ones and keep it at this, right? So we have our add 2 to S64, which fails if we pass the wrong thing, and which will succeed if we pass the right things. Obviously, there is a ton that actually can also be done here, but this is just a generic idea of parametric polymorphism. You pass in type, and you use that type inside the function or inside the template of the function to add some constraints to it and make the implementation. Okay. Ad-hoc polymorphism is more funky. And I'm not certain how far we will get with it today, but I will try to create something interesting for us. So the first thing to know is that ad-hoc polymorphism, since it's otherwise known as overloading, means that we need to somehow have multiple functions that are known under the same name, or in our case, that are known as the same value. There are multiple ways how we can approach this. I think the easiest one would be for us to introduce a separate type that is going to be a function, how should we call this? Function overload set. And this type will essentially contain multiple functions that we will choose depending on the arguments that are going to be passed to us. So again, like how do I want to approach this? I guess we will need one of these as well. So descriptor function overload set. And instead of this argument list, we will just have overload list, and it's not value, it is descriptor function, I guess. Is it just descriptor or is it a value? No, it should be a value. Yeah. And we have overload count as usual in C to denote how many of these are here. Now we need to add it to our list. Overload set. And I'm not even sure I'm going to keep this, but I want to kind of go through the motions and show what it would entail for us to have something like overloads. Okay, we have overload set. We are obviously not using it, but we will. let's do just that. Okay. So we obviously need this overload set, or more precisely, we will need a value that will hold this set. So we say value overload, and then we start. So we need to have a descriptor, which is going to be overload descriptor, like so. The type of it will be this, right? And then overload set will be something. So, and that something means we need to have value overload array, which has this stuff. And here we would put our functions. Actually, the type of this needs to be this, right? It's a array which takes one star, and then we will store pointers to values as the other thing. Now we just need those values. We can very easily produce a couple of functions. So let's create two of them, and we say that and we will kind of create a function where we can pass a value, and it will give us back the size of that value in bytes, at least two of them. So we have a function called size of S32, and that function will return to us 4, right? Because 32 bits, 4 bytes. And then we have size of S64, and this function will return 8. But it needs to have an argument, even though it's not going to use that argument for our overload resolution to work. I mean, we could also like do some operations on it, but it doesn't really matter what we do. I just want to have something super simple, and this is the easiest I could come up with. So we say arg S32 of x, and we are not using x. The same here, it will be arg S64 of x, and we are not actually using x, we're just returning it. Okay, now we put this into our overload array. So we say size of S32 and size of S64. Okay, now we will use this in here, what it's called, overload list, overload count. Okay, overload list is overload, maybe I should call it list for consistency. And overload count is static array size of overload list. Static array size is just a macro in C that you can easily write that allows you to not hard code like number 2 here, because compiler actually knows what is the size of this array. Okay, so we have our descriptor. And we need to have an operand. And operand for this will be kind of funky because we don't actually have an operand, right? The operand for a function is supposed to be address of that function, but for overload list, we don't have an address because it can be one of many addresses. So I guess we will just say 0, right? We don't have an operand. So whoever will deal with this will need to deal with it. Okay. Good, we don't need this, I believe. This needs to be descriptor type. Okay, let's first check that we are compiling. Initializing compatible types from value star to descriptor star. Okay, so this is fine. Now we need to actually use it. And how can we verify that all of this works? Well, we need to call this. So we need to have another function, like that function that will be called checker. And that inside of that function, we will be, how should I do this? We'll need actually two functions, sort of. Or we can sum here. I can sum here. So what we will do is we'll say value star A is this thing, which we'll call our overload with S64. And then we will have B that will call overload with S32. And then we say return plus a B. So what I would expect to happen is that if we do value as a function, and so what is that? Already forgot function type. Yeah, this is how we do it. Function type, yeah, void to what? We are returning S64. That's fine. So it will be void to S64. And this is checker. Okay. We can say function type. So we save it to the variable. Let's call it checker value. And we do our check. Check that checker is 12, which is what it should be. We return 4 here, we return 8 here, and we call it once with 64 and once with 32. Okay. Let's see if that builds it all. Apparently I'm using value as function somehow incorrectly, so let me check. Basically it's the other way around. It should be like so. Okay. If I try to run this, it will explode horribly, but let's see it happen. So where it explodes right now is inside call function value, because call function value, where are you? Call function value. Here you are. So call function value expects this to be a function, right? So this assertion actually fails. Since it is not a function anymore, it is an overload set, we need to do some funky stuff. So first of all, I will need to have a forward declaration of this, because I will need to call it more or less recursively. And now I say that if to call descriptor type is descriptor type function overload set, then return call function overload set and pass all these and just over here, right? So builder to call argument list and argument count. This is what we do. Now we will need to have this function overload set, and it needs to do some stuff. Okay, what does it need to do? Well, it needs to go through the whole set of functions and check if we find a match. And if we do find a match, well, that means everything is fine. For that, we need to basically take this code. I could abstract away, but for now, let's just copy it. Let's rename this I to something more speaking, calling it arg index, because we'll have two nested loops here, and it is very, very confusing if you name your index I or j, and in those cases. So S64 overload index is 0, overload count is overload index is less than to call overload is a descriptor. Yeah, I guess it's descriptor overload set. Let's actually extract this and say that overload set is this. What's the type of it? Descriptor function overload set. Okay, descriptor function overload set is this. It's also right now a bit weird because we have like values inside of a descriptor now, which is not very good design. So it will probably be a prime refactoring topic of like how to better structure this kind of stuff. But that is gonna happen later. So we have overload set, and now we can iterate over that. Overload count plus overload index. Now we say that value star overload is overload set overload list of overload index. Lots of overloads in that thing, right? And now we need to do this, right? So for every overload, we need to go through all of the arguments, but instead of asserting and instead of moving, we just say that if not this, yeah, that's correct, races. So if they are not same, then we break and we say bool match true. This is already the same type as what we do when we encode the instructions, right? This is the same type of loop, but now for functions. In a sense, we could consider at some point to replace that encoder with just a function that accepts like an overload set function. Maybe that would be an interesting thing, but that is definitely something for later. Okay, so match false, and we say here if match, then we return call function value. Function value, and what we pass in now is this overload instead of our original to call. So we duplicate all other arguments, but we now call a very specific function. And if we got to here, that means no matching overload found. Good. I think I need to update some stuff here. Yes, I do. So first of all, we need to add some assertions. The first assertion is about the type. Even though right now we call this function only from one place, who knows from how many places we're going to call it later. So that's a good assertion to have. The next thing is we need to extract the function descriptor, and that happens like so. And we're probably ready to try to build this. So it's a descriptor, I believe like so. Yeah. Good. So we have some code. It does something. Let's see if that actually works. And voila, we have a winner. So this is basically all there is to it about ad hoc overloading. Again, it can be complicated if you like start mixing different parametric and ad hoc overloading, for example. It can get complicated if you start to introduce extra constraints on how you decide to choose which overload to use. You can have issues if you have default parameters, because, for example, like two different overloads can match the same thing. So you have to start thinking about like which one to pick, and there are different reasoning you can apply for picking one or the other. But in essence, this is it. This is all it takes. You shove functions into overload set, you verify that they are like, you find the one that matches, and you're done. So here we go. This is ad hoc polymorphism, otherwise known as overloading, and this is parametric polymorphism, which is we now have both of those, sort of. We could easily mix and match that, right? Because since we could just take this code, shove it into a function, and pass a type to it, and use the type here somehow, and we would have all the stuff we want. So with that, thank you very much for watching, and hopefully see you next time.